Hi, welcome to a Physionic detailed study analysis. We're going to be going over a number of different studies, really specifically scientific reviews and meta-analyses, to distinguish between two prevailing models of obesity. So one is called the carbohydrate-insulin model of obesity, and the other one is called the conventional model. And they're both espoused by two different groups of researchers. Most researchers, just in general, outside of these two groups, tend to follow the more conventional model, hence the name conventional. But there's also some researchers that follow the carbohydrate-insulin model, and we're going to see why, because they're going to be presenting, or I'm going to be presenting on their behalf based off of what they said in these scientific reviews, the evidence for their stance. So if you're interested in that, as well as some applicable takeaways, then stick around. If you're not familiar with who I am, my name is Nicholas Verhoeven. I'm a PhD candidate in molecular medicine, and this is what I do. I read research, distill it down, or break it down, sum it up for you without losing too much of the detail, so that this doesn't turn into a pop science channel. So you actually get a full education on the topic. So with that, let's open this can of worms up, because this is quite the debate between the two sides. So as I mentioned, we're going to be going over the carbohydrate insulin model, as well as I guess I should remove myself there for a second, as well as the conventional model. So I'm going to explain what each one of them are, so understanding the CIM model as well as the CM model. Then I'm going to present you some of the evidence in some of these scientific reviews for the carbohydrate insulin model, as well as rebuttal by the conventional model, so the researchers of the conventional model, and then some agreement where they end up slightly agreeing, as well as some disagreement. And I'll also be going over some of the mechanisms, some of the physiological mechanisms that are proposed. And for my Physionic insiders, well, you'll also get access to the applicable recommendations. So I'll be giving 6, potentially 7, but 6 for sure, recommendations that are offered by the carbohydrate insulin model. So if you end up listening to this and thinking, oh, well, this I follow more of the carbohydrate insulin model, or if you already feel that way, then I'll be giving you applicable takeaways on what you could do to potentially implement in your nutrition after you speak to your nutritionist, dietitian, doctor, et cetera, et cetera. But I will say that these recommendations, actually, I would probably also just second, regardless of whichever model that you end up following. So if you're interested in accessing this full study analysis, including the Insiders edition, you can join the Physionic Insiders, where you'll get access to, obviously, this study analysis along with many, many other study analyses, summaries, seminars, live sessions with me, and a bunch of other good stuff. But if you're just interested in these, let's move along. All right, so as usual, I'm displaying the different studies, which again, are, like, some of them are meta-analyses, so yes, they're studies, but some of them are just scientific reviews, which is just a situation where a researcher essentially just discusses, they just talk through all the research and they just cite the research, but they're just essentially making an argument. They're like a debate format almost. So it's just them writing out their thoughts and just inputting different scientific information, different studies to substantiate their points of view. So we've got one for a review of the carbohydrate insulin model of obesity. This is actually pro-conventional model. Then we've got a rebuttal, or not really a rebuttal, but these individuals, so Ludwig and Ebling, are the ones that are the research group that believe in the carbohydrate insulin model. Dr. Hall and Guillenet are the ones that believe in the conventional model. And certainly I'm not going to be covering everything that they have to say, but I'll be covering a good portion, so you'll get a pretty good understanding of both models. So these two are reviews. Then we've got one more review here, and then we have a meta-analysis, and then a reanalysis of this meta-analysis, and then we've got a editor's comments, so a commentary on this reanalysis. So there's a lot of back and forth that goes about. So hopefully I'll be able to do it justice in explaining everything. Now, in terms of funding, nothing really pops out. Some of them have no funding because it's just sitting behind a computer and just spending some time to analyze data. Other ones, like the reviews, typically there isn't any funding, but sometimes there's some public funding. What I mean by public funding is that it's government, it's people paid funding, so there's no industry funding of any sort. And then there's one with nonprofit funding, which ended up paying for a study that was performed by Dr. Hall, so part of the conventional model, but this nonprofit actually believes more of the carbohydrate-insulin model. So it's like opposing forces. So they funded a study by researchers that ended up being convinced of the opposite conclusion, if that makes sense. So it's like the most problematic funding that you could possibly have in a weird way. But it probably had no effect here anyway, regardless, even if it was industry funding. I mean, I don't know what, big keto, big carbohydrate. So anyway, the funding sources, you can see there isn't any issue if you believe funding source is a huge issue. All right, so I'm going to introduce you to each one of these, and then I'm going to go into more detail on each one. So generally, kind of the mechanisms of what they think, how we end up developing obesity, why we end up gaining fat over time. Let me remove myself real quick so you can see. Okay, so the carbohydrate-insulin model. It starts out with, I guess you could really pick any place to start out, but let's start out here with the dietary carbohydrate. The idea is that if you consume dietary carbohydrates, you see an increase in insulin secretion, which makes sense because carbohydrates are the most potent increase in insulin secretion, which then leads to fat storage because it specifically, one of the main tenets is that it partitions the nutrients, meaning that the nutrients that are found in the bloodstream, so let's say the carbohydrates, the fats, etc., are moved into the fat cells. So that, and I'll show you a diagram of this in the next slide, but you consume carbohydrates, insulin levels go up, the nutrients that you just consumed with the carbohydrates get shuttled into the fat cells, leaving the blood vessels essentially bare. I mean, quote unquote bare. They're not completely bare, but they're lower than where they should be, which leads to circulating metabolic fuels being lower. So like glucose, blood sugar, and lipids that are found in the bloodstream are lower because they've been sucked up by the fat cells due to insulin secretion, which then leads the rest of the body to be in a quote-unquote starvation state, which then leads the rest of the body to then signal to the brain, which is where we get our hunger signals, to the brain to then increase energy intake. And then that's where we get hunger, obviously, and we start consuming more food. This probably should have pointed towards hunger and then energy intake, but regardless. So then you end up consuming more and then you start gaining fat. So it's not about the calories, it's not about the substrate itself that's leading to fat gain. It's more about the carbohydrates specifically leading to insulin, leading to some fat gain, which then pushes everything more towards consumption, so consuming more. And additionally, you get a drop in energy expenditure because the rest of the body is in this quote-unquote starvation state. It increases muscular efficiency, which we see that in metabolism in general. You see greater levels of fatigue and resting energy expenditure. Now, I would like to point out here, I mean, I'm certainly biased. I have leaning towards one model. So certainly take this with a grain of salt, but or many grains of salt. But one of the issues here is that if we start describing these mechanisms, we have to actually have proof, because a lot of people will say, well, wait a second, I eat carbohydrates and I feel sluggish, and I feel like I'm fatigued and I have and I gain weight and all these different things. It makes sense. Like it actually makes sense in terms of a personal perspective, but does it actually bear out in the research? Because just because mechanisms make sense doesn't mean that they're actually correct. They can make sense and be incorrect, but the overall effect, so you gaining weight, you feeling fatigue, can also still be correct, which I actually have a video releasing on this very topic very soon. So I'll leave it for that. But the point is that you have this drop in circulating nutrients. So it's not necessarily overconsumption that leads to fat gain. It's the fat gain that leads to the overconsumption. And then it's a cycle. It just continues that way. So to illustrate this a little bit more, so let's say this is coming from your intestinal tract. This blood vessel is coming from your intestinal tract. It's filled with nutrients at this point. So we've got our triglycerides, we've got our fatty acids, which I don't have displayed here, and we've got our glucose levels. And you can see it's pretty dense here. There's a lot. But with these carbohydrates comes an influx of insulin, obviously, from the pancreas, which then shuttles all of these nutrients into the fat cells, or most of the nutrients into the fat cells, leaving downstream fewer nutrients in the bloodstream, which then leaves the rest of the body to be devoid of nutrients, and therefore they start sending out signals of starvation, hunger to the brain, which then leads to overconsumption. So the brain registers, okay, we're low on nutrients, even though the fat cells are gobbling up as much as possible. So they are growing, so you're getting fatter, but the rest of the body is starving, which then leads to more overconsumption. And then this occurs again, the fat cells grow, and it just continues. It's just a perpetual cycle over and over again. Now, the conventional model is the exact opposite. So it goes in directly the opposing direction, talking about obviously calories in, calories out, but it's certainly far more complex than that. So they're talking about overeating ubiquitously tasty foods, so usually like ultra-processed foods, foods that are highly palatable, hyper-palatable, which then lead to overall energy intake, which then increases the circulating metabolic fuel. So if you'll allow me to go back here. So getting up to this stage, and then that gets stored in fat tissue, but it doesn't specifically get stored just in fat tissue. It just gets stored in fat tissue as just one consequence. And then, of course, independent of overeating, there's also reduced reduced physical activity or greater physical inactivity, which can also contribute. But I think personally, I would argue that the greater issue is the overall energy intake, and I'll show you some data on that as well. So it's not specific to fat cells, but it does still affect fat cells, because if you're continuously consuming, those excess nutrients have to go somewhere, and they go into our fat depots, because that's the primary area where we can actually store this excess level of circulating metabolic fuels. Okay, so now to get into the evidence for the carbohydrate insulin model. And I'll go ahead and warn you, I'm going to have a few problems with some of the evidence. Some of the evidence I think is really good, and I'll point that out. So I'm, again, just indicating this is, I guess you could say it's my bias, but I think that the points that I'll bring up are good points. So it's not like I'm saying, no, I don't want to believe this. I've seen so much contradictory information that would dispel much of the information that I'll be going over here. Not only that, the evidence that they purport as this is evidence for the carbohydrate insulin model, I can tear it to shreds, and you'll see why. So that's my disclaimer, and if you feel like you disagree 100%, please let me know. I'd be happy to discuss it. But just say like, well, this is how I feel, and this fits my circumstance. That's not a good scientific argument. You have to bring data to the table to be able to, or fight against, like have some sort of explanation for why the data is the way that it is, which is what you'll see me do here. So a lot of this information comes from this scientific review. So the carbohydrate-insulin model of obesity, beyond calories and calories out. I forgot to mention I forgot to add this, but there's an illustration where they, in the very first few sentences, they describe what the calories in, calories out model indicates. And I just kind of had to like slap my forehead. I was like, that's not what the calories in, calories out model is. So they, right off the bat, just mischaracterized the calories in, calories out model. But I digress. Let's just move on. So I've picked out, these aren't complete study analyses. That's why I haven't included it in the number of studies, mainly because I would have to go through, obviously, the baseline measures and go through the study design and all these different things, which we have a lot of data to go through. So I'm not going to be doing that. But I did want to pick out the data that they cite. So they say, in a sentence structure in this review, they end up citing, okay, well, this study showed this effect. So I wanted to show the effect so that we can actually see it for ourselves. So I'll have the study that they cite up here in this review, and then I'll just pick out a few of the pieces of data so that we can actually look over them for ourselves. So one of the things that they mention is that fat gain was greater when animals, so this is an animal study, were injected with insulin. And so one, weight gain was increased over time. So we've got our time, we've got our weight gain. So this is not specific to fat. Fat is over here. So this is just weight gain. And they've got a few different measures. We don't need to go into like what CDP is because we don't care. We just care about the comparison between saline and insulin. So saline is essentially no insulin, but it's still an injection. And insulin is obviously an insulin injection. And what we see is that with each one of these treatments, as these rodents, I think they're rats, maybe they're mice, end up consuming over time, they gain weight. So fair enough. I mean, that's fine. But there's no difference in weight gain at the end of the 30 days of measurement. Now, in terms of fat deposition, however, there is a difference. And we can see that by these bars right here. So these are different sections of the body. So dorsal would be like the back, for example. And they're just dissecting different sections of the body and then measuring how much fat is there. So here we've got our insulin condition. It's kind of hard to distinguish the two, but this first one is the insulin condition. This second one is the saline condition. And that's really the ones we want to focus on. I mean, we can also look at this black bar, which is also insulin, but it's also with the addition of another drug. So it has a confounding variable in there. So we're just going to throw that out for the time being because we don't need it. It indicates the exact same results though. So with insulin alone, we see that there is an increase in fat in this epididymal section or this perirenal section. We continuously see the insulin bar is higher and statistically significantly different from the saline bar. So this is proof that insulin, if you inject insulin, that yes, you see increases in body fat. Okay, great. So this is one piece of evidence that they cite, but there are no differences in weight gain. Another thing, so I wanted to point this out specifically because they end up citing some more research that's kind of in conjunction with what we just went over. They say that analogous to the insulin administration studies, calorie restriction to prevent excessive weight gain in animals on a high glycemic index diet, so GI is glycemic index, did not prevent excessive adiposity or the associated cardiometabolic risk factors, findings for which the conventional model has no explanation. So we're going to go over one of the studies that looks at the high glycemic index diet foods. So they're also distinguishing, the point is here that they're also distinguishing between low glycemic index and high glycemic index. And they're saying it's especially destructive to be consuming high glycemic index diets. You have to excuse the train that just went by. It's kind of a pain sometimes. Sometimes they just lay on the horn for like 30 seconds straight as if people can't hear them. it annoys me, but whatever. Okay, so another piece of evidence that they cite is looking at a ketogenic diet fed, again, this is in animals. We're going to get to some human data as well. But the ketogenic diet inducing specific metabolic changes to these animals. So they had some animals, we're going to start over here and then I'm going to walk you over here. They had animals on a normal chow diet. They had animals on a high fat, high carbohydrate diet. So it's kind of a combination. It's supposed to make them gain weight. A ketogenic diet, which is obviously almost no carbohydrates, so it was extremely, extremely low and high fat. And then a chow diet that's calorie restricted. So they specifically restrict the calories. Now, they cite this study and they're specifically citing this piece of information here because this is a measure of heat. So it is a measure of metabolic rate, essentially. And why they would use heat is because I know people, I don't know, for some reason, if people just don't seem to believe that calories are something that some people, I'll say some people don't seem to feel like calories is actually a thing that we need to worry ourselves with. This metabolic measure is a measure of calories. That's exactly what it is. So if you were to put an animal or a human into what's called a direct calorimetry chamber, then all the heat that they produce is a measure of calories. It's a proxy measure of well, it is a measure of calories because calories is a measure of heat, which is a proxy then of ATP use or cellular energy use. I'm not going to go into too much more specific on that, but I'll be sure to release some videos on that as well because it's really a concept that I think most people talk about calories and they have no clue what they're talking about. And it kind of baffles me. Maybe it's because of my metabolism background that I just understand it, but people seem to think, well, calories don't exist because they're heat. So therefore it has nothing to do with food. It's like there are metabolic pathways between those 2 points that bridge that gap and make complete sense. But anyway, I digress. The point is they're measuring heat because they're measuring metabolism. So they're measuring the overall caloric yield. And as we can see here, you don't need to see it in too much detail. I probably should have made these a little bit larger. But the top one is an overall measure of the ketogenic diet, so right here. And you can see it's a little bit higher than all the other conditions. The other conditions lag a little bit behind from this point all the way to about this point. And in total, they end up calculating it to about an 11% boost in metabolism. So the point is eliminating carbohydrates and increasing your fat intake led to an 11% boost in metabolism, which is really intriguing. And it's one area where I changed my mind, which is something that, as I mentioned, I follow a more conventional model style of thinking. But after seeing this data, as well as some of the data that I'll be presenting in just a little bit, you'll see, or at least I think you'll see, that there's some evidence that this might actually be the case, that with a ketogenic diet, you might see increases in metabolism. Now, I'd like to see more data on it, but as so far, I'm leaning now more to, before I leaned that's not the case. Now I'm leaning towards, yes, that is the case. So this was an interesting finding that we see this 11% boost in totality with the ketogenic diet. However, there were some issues that I had with this because if we shift over here, this is from the same study. If we shift over here, remember one of the things that the model mentions, so if I can go back up here real quick, is that it leads to hunger and energy intake if you are eating dietary carbohydrates. Well, allow me to mention that these diets, the high fat, especially the control diet, they're like 50% carbohydrates. Okay. So why don't we see an increase in body weight? Secondly, when they measure caloric intake we can see that the chow, so the black bars here, are no different from the ketogenic diet. I realize this one is way higher, but this would indicate that there's increased consumption with the ketogenic diet, but that's not what I'm saying, because there's no statistical significance between these two, and that's probably because these error bars, these standard deviations, are wildly huge. So overall, the point is, how to read this is that there's no statistical difference between these conditions, okay, in caloric consumption. But they're consuming, in the ketogenic diet, these animals are consuming no carbohydrates essentially. And in the chow condition, they're consuming a massive amount of carbohydrates. So you would predict, based on this model, that there would be an increase in caloric intake, but there isn't. So the very study that they cite as proof of their concept, again, indicates that that is not the case. So I just wanted to point that out, because there's some within their own evidence, there are inconsistencies with their own hypothesis. Now, another study that they cite, which I thought was really interesting, is this one, where this one was in rats. So they had rats on this is a comparison of low GI versus high GI foods, which kind of goes back to this statement right here. So prevent excessive weight gain in animals on a high GI diet. And I think they're referring, I believe, if I remember correctly, they're referring to this one, because at this arrow point, they end up reducing the caloric intake of the high GI condition just a little bit to make sure to control for weight gain, if I remember correctly. And so we've got a high GI, meaning that high glycemic index, meaning that they're consuming more sugars, more simple carbohydrates, and the low GI is consuming more complex carbohydrates. Now, this is not a comparison against a no carbohydrate condition. They're still, both groups are consuming carbohydrates. So now we're not getting into as much of an apples and apples comparison against low carbohydrate diets, because there is no low carbohydrate diet here. They just want to distinguish, is there an effect of high glycemic index versus low glycemic index carbohydrates? And that makes a lot of sense, because you want to know if there are differences within a group, within the carbohydrate macronutrient group. Do you see changes? So what they found is that weekly food intake decreased slightly for the high GI group, because again, they specifically forced them to consume less. Yet their body weight didn't change a whole lot. And which was really it threw me off. I was like, what's going on here? And if we look at, for example, their body weight, it's roughly the same. However, what their point is the body fat levels were so much higher for the high glycemic index group. It's 97.8 compared to 57.3. And yes, it is statistically significantly different, which makes a lot of sense. So here they're showing that high glycemic index foods specifically have a fattening effect. However, and we can see that according to multiple fat mass measures. So if looking at different sections of the fat, all of them are higher or mostly all of them are higher in the high glycemic index foods. Adiposity is obviously much higher. However, here's where I have to put something in, because in the calories in, calories out model, they are at this point controlling or trying to control for the calories inside of the equation. And then they're making conclusions based off of just controlling one side of the equation, but they don't control for the calories outside of the equation. And we can see that lean mass is significantly decreased in the high glycemic index animals. So that there is a statistical difference, meaning that it's possible that some of their lean tissue, so like cartilage, bone, muscle, I'll bet you muscle is probably one of the big ones, as well as cartilage, probably not so much in bone, was decreased with the high glycemic index condition. Now, You could certainly blame that on the high glycemic index foods, but most likely, if I had to take an educated guess based on about 100 other studies, that at the very least, the greatest factor is the underconsumption. So forcing these animals to consume less, which ultimately leads to, if you do that long enough, that leads to lean mass loss, especially if you're not using it much. So this is one piece of evidence that I would say, well, maybe their caloric expenditure was decreased as well. Now, on top of that, they didn't measure caloric expenditure. So we can't actually say anything. We can say off of this that, yes, the high GI foods led to more body fat than the low GI foods, but we can't necessarily say that this is a proof against the calorie model or the physics of the situation, because we don't have a measure of the other side. And they actually mention this in this study. The researchers point out that, it's possible that there was a decrease in these rats' activity level because rodents have a very peculiar, or I shouldn't say peculiar, but just a different style of activity level. As in, I believe, if I remember correctly, at night they are extremely active. Don't quote me on that. It's one or the other. Either during the day they're extremely active, or at night they're extremely active. And then during the day they're extremely sedentary, or at night they're sedentary. But it's a stark contrast, like huge differences in activity level. So I'm not saying that this data is incorrect. What I'm saying is that there are other considerations that were not measured. And without those measurements, it's difficult to look at this and say, oh, well, we're just going to ignore these confounding variables and just make the assumption that calories don't matter in this situation. So it's just something that I wanted to point out. And of course, this doesn't actually, the other thing is it doesn't speak to, if I can once again go back to this model, this is dietary carbohydrates. There's no mention of high glycemic versus low glycemic. They're both carbohydrates. They both lead to much higher insulin levels compared to like fat. So I guess my issue with this isn't actually a discussion of the carbohydrate insulin model. This is more of just a discussion of high glycemic versus low glycemic, which is totally fair. I think most people would agree that high glycemic foods taken in isolation could be detrimental, could lead to adverse effects that you wouldn't normally see. But since there's no comparison against a low carb condition, this doesn't tell us anything in defense of the carbohydrate insulin model, because they're both carbohydrates. Just another point that I wanted to throw in there. Another thing that they mention is this study, which is a Mendelian study, which I really love these studies. And they're essentially looking at a population. So they're looking at a sample of thousands of humans. So this is a human study, thousands of humans. They're looking for what are known as single nucleotide polymorphisms, which are essentially these miniature mutations that occur, or anomalies that happen in our genes. And they're looking for specific genes that are related to insulin secretion. And they're trying to identify if we segment people based off of, do they have these SNPs, these single nucleotide polymorphisms in these genes that then lead them to have higher insulin secretion? Is that then associated with greater BMI, so greater body mass index, greater body fatness? And what they find is that, yes, there is an association between these genetic variants, these SNPs, and insulin secretion. So the greater level of insulin secretion you have, the greater association you have, or you have an association, I should say, with BMI. So this is a really interesting study. It's cool to see, but it's still an association. So because the Mendelian randomization, if you've heard me speak on this before, is specific to the trait It's not specific to the BMI. So it's telling, but it's not a all-out cause and effect kind of scenario that we're getting from this. Another one is another thing that they mentioned here, which I found, I actually was kind of incredulous when I read this. So of note, 2 major trials that employed special measures to improve compliance. So the Diogenes and Direct trial found greater weight loss on low versus high glycemic diets. I don't think anybody would agree or disagree, I should say, disagree with that. I think there are plenty of trials that show that if you're consuming low glycemic load diets compared to a high glycemic load diet, typically you would see greater weight loss with a low glycemic load diet. I think most researchers would agree with that. So that's not a point of contention. Especially if you don't actually control for calorie consumption or food consumption as a whole. However, what really threw me off is when they say a third major study, Diet Fits, reported non-significantly more weight loss on a healthy low carbohydrate diet versus healthy low fat diet. But both groups were counseled to avoid refined grains, sugar, and other processed foods. Okay, so both groups were counseled. That's fine. However, I'd like you to pay attention to how they say this. Reported non-significantly more weight loss on a healthy low carbohydrate diet. If you look at the data, that's not what it shows. This is a crafty way of saying this. Okay, so I looked at the data, and so this is the Diet Fits study that they cite. And if you look at the weight change, so this is a healthy low-fat diet, so higher carbohydrate, and then we've got our healthy low-carbohydrate diet. And this is with all the participants grouped together after 12 months. So after 12 months, how much weight did they lose? And the weight difference, the weight loss difference was not different. So is slightly higher for the healthy low carbohydrate diet, but it's not statistically different. So that's one way of saying reportedly non-significantly more weight loss. But typically when you report this kind of stuff, you don't say it that way. You say there was no weight loss difference between healthy low carbohydrate diet and healthy low fat diet, as the difference was non-statistically significantly different. Something along those lines, not saying, yeah, there was more weight loss, but it just happened to also be non-significantly different. It's just a crafty way of writing that, which made me chuckle. And then they also determine which another reason why they mentioned this study is because they are also looking at the level of insulin secretion. So they're breaking, so this is the overall effect. So 2 groups, everybody grouped together, and then the healthy low carbohydrate group, everybody grouped together. And then they break it up into 3 different subgroups. One subgroup releases low levels of insulin, so is low insulin secreting group. They've got kind of a middle group, and then they've got a high insulin secreting group. So if you give these people glucose, sugar, carbohydrates, then what level of insulin secretion do they have? And they end up creating these cutoff points and then segmenting everyone into these 3 groups. Then they analyze it based off of how much weight change that they have to relate it to the insulin secretion, to see if you secrete a lot of insulin just normally, then do you have more difficulty losing weight, 1, and 2, do you see a benefit to being on one diet versus another diet? And remember, both of these diets are supposed to be as healthy as possible, as in they're avoiding refined grains, sugars, and other processed foods, or at least that's how they're counseled. And there's if it's the low insulin secreting group, there's no difference. I mean, maybe you could say there's a slight shift for lower, like a slightly greater weight loss in the low carbohydrate group, but it's not statistically significant, probably not even close. The middle group is, again, similar story. But then what was intriguing is what a lot of people believe, and what even this model espouses, is the fact that if you can secrete a lot of insulin, then you are more prone, or you would be better off by consuming a low carbohydrate diet, which is similar to what they say here, right? If you have higher insulin secretion, then you have an association with greater BMI, although the measures aren't exactly the same. And what they found is that there's absolutely zero effect. So that is not a factor in this, according to this study. If you consume a low-fat diet or a low-carbohydrate diet, both of them will lead to equal amount of weight loss. So this, again, it's interesting that they would use this study as a proof for their perspective when it actively disproves their perspective. And then they only focus in on this one difference between these two, but it's non-statistically significant with a really high sample size. So, and I mean, beyond that, even if we were to not even harp on that, let's just let that go for a second. If we were to just focus on this, why did the carbohydrate group even lose weight? They're consuming mass amounts of carbohydrates. So why would they lose weight according to this model? Like, there's so many things that just don't make sense. You kind of get where I'm going with this. Like, there's a lot of things that if you were to just focus in on one, just a tiny comment and say, oh, well, there's the proof, that's fine. But then you just extend your view a little bit outwards, not even to other studies, within the same study on multiple occasions. And there are inconsistencies with that same proof. That's my point. Hey, I hope that you're enjoying the video so far and you're learning some. Hopefully I'm not getting you too riled up. I just wanted to mention that, again, that if you want to actually get the applicable takeaways based off this, well, really based on both models, then you should join the Physionic Insiders. As well as in the Insiders, there's these live sessions, which I'm actually going to be doing a live session on this topic so that you can join in and ask questions, offer some critiques, things that maybe you would want me to cover. We can maybe have a little bit of a dialogue back and forth to discuss some of these things. So I have these office hours, that's what I call them, these sessions where people throw in some questions to me, and then I take about a week to research a little bit into them, and then I create a presentation that's a very loose structure. It's much looser than any of my other content, and it's just like a powwow, just people getting together online, and we end up discussing some of the research. So if you're interested in accessing all that, as well as my seminars, as well as all my study analyses, as well as research reviews that I release pretty regularly, and these condensed summaries, so you don't have to go through the entire video if you're not interested, then you should join the Physionic Insiders. I'm sure it'll be a great benefit to you. Okay, back to it. All right. Now, I've been talking a lot about the carbohydrate-insulin model. I'd like to go now and discuss the conventional model and essentially what they believe, but then also go into some of the rebuttals that they've presented. So again, these are two research groups going against one another in terms of what they believe. Remember, just as a reminder of the conventional model is that people are overeating due to ubiquitously tasty foods. I'm going to go into a little bit more detail on that in just a little bit, which leads to overall energy intake, an increase in energy intake, which leads to circulating metabolic fuel. So you have elevated levels of these nutrients, which ultimately get stored in body fat. And over a 24-hour period, if you have circulating metabolic fuels that are higher than where they should be, then they have to continuously be stored into body fat. So you eventually gain weight and you gain body fat. Another part of the equation is energy expenditure. I personally, as biased on my side, I don't think that this is as much of an issue. I think the greater issue, because it's so much easier to eat the calories, to eat the nutrients, than it is to expend the nutrients. If you go for a walk, it's like 80, 100 calories for a mile's worth of work, but try eating 80 to 100 calories. It's so easy. So I think that this is the larger issue, but they also mention physical inactivity. So it's certainly easier to understand, but it's the exact opposite of the carbohydrate insulin model. So one of the studies that they reference is this study which is actually a review. It's a scientific review by Stéphane Guyenet, which is one of the researchers that is involved in purporting this conventional model, and he ends up tracking or showing the data on the overall caloric consumption over time. And he indicates that since about 1975, 1980 or so, we've started to see this increase in caloric consumption, so that we're consuming 425 calories more a day, a 20% increase since then. So you can imagine that 425, that's on average. Of course, some days you'll be consuming 50 calories less than your baseline, than your maintenance level. Some days you'll be consuming 600 calories more. But on average, that's the idea. So the idea here being that over time, we've been consuming more and more calories. So to get a little bit more mechanistic about how they present this is from the same review. We're going to start with these. Well, we'll start here. So you've got these different factors that influence your brain. This model is more brain-centric, and the other one is more fat-centric. I tend to be more in the middle, but as they describe it, is that it's more brain-centric. So there are different environmental factors, so like eating processed foods, hyperpalatable foods. The could be cultural, could be because of the foods that are consumed in a particular culture. There's all kinds of different factors, different variables that could affect how we react to food. Then there's a genetic component. Certainly some people have genes that predispose them to hyperphagia, for example, or overconsumption, or it might be something related to insulin secretion. They might feel really jittery if they consume too many carbohydrates. I don't think that this model nullifies the idea that if you feel better consuming lower carbohydrates, that they're not saying you have to consume carbohydrates. They're just saying it's not the only way to go about weight loss or fat loss. And then another one is neuronal injury, which is very specific. So really the big two for most people is probably these, with the majority of individuals falling into the environmental factors. So this affects the brain, which we're going to skip over that for a second. I'm going to come back to the brain. So that leads to food intake. So food intake leads to nutrient absorption. We get satiating signals, which we'll touch on, which occur in the brain. So we consume food, nutrient absorption goes into our bloodstream, ends up at our fat cells, or some of it ends up at our fat cells, gets stored as energy, and then the fat cells then lead to a secretion of leptin. Additionally, we can also, if you consume carbohydrates, you're getting an influence of insulin. And these hormones, along with other hormones, you could talk about things like peptide YY, you could talk about ghrelin, you could talk about a lot of other hunger hormones specifically, but one of the big ones is leptin, certainly, can affect the brain. So when leptin levels are high and it's interacting with the brain, specifically the hypothalamus of the brain, then you get a reduction in hunger. You get an increase in satiety. You tend to feel more satiated. You get more signals. And you also tend to see increases in energy expenditure. So, which then reduces energy storage because you're expending some of that energy. However, if leptin levels are low, so you're under consuming, right? So if you're consuming less food than what your body needs, then energy storage, the fat cells start to reduce their leptin release, which then is sensed by the brain. The brain, the hypothalamus again, starts to release more hormones that are, and by these hormones, I'm talking about like AGRP, talking about neuropeptide Y, talking about even like peptide YY. You start to see these differences in these different, these brain-centric, but they affect our feeling of hunger and whatnot. So leptin levels are low, which leads to greater release of these AGRP and neuropeptide Y hormones, which then leads to greater levels of hunger, and therefore we start to see a drive to eat more. So to then fulfill that energy state and then to get those increases in leptin. So there's certainly there's a huge hormonal component. It's not like, oh, calories in, calories out. Why aren't you skinny? It's not that simple. The point is, though, that the calories matter. They are the backbone, but there's a lot of physiology that's stacked on top of that backbone of calories in, calories out. Calories in, calories out is sensed by your fat cells as energy storage is low or it's high. But the leptin and the insulin and all these different hormones that I was just describing, those all play a factor in terms of your drive to consume, your satiation signals, as well as your genetic predispositions. If you are, for example, leptin resistant, that is a possibility, especially in severely obese individuals. They can start to become leptin resistant, where their leptin levels are high, which would normally indicate the brain, hey, stop eating, but the brain has reduced the number of, or the effectiveness of the receptors, the leptin receptors. And therefore, even when the internal physiology of the rest of the body is fine and it's saying, hey, we're full, the brain is still sending out signals of continue to consume. So there's a lot of different factors, but the backbone is still that food intake, calories matter the most, and then there's a bunch of other steps afterwards that need to be taken into consideration. And they mentioned this, I believe this was a study where they looked at the overall change in body weight. So if you reduce your energy intake, so just cut your calories over time, and you start to consume more, what happens specifically to energy expenditure, but also even more important, what happens to appetite. So these are in relation to body weight. So you cut your energy intake. Let's take this one step at a time. You cut your energy intake. Your body weight starts to drop. Everybody experiences this. If you're truly cutting your energy intake, you are losing weight. So you start to lose body fat. Okay, great. But then you start to creep upwards. So you're still in a caloric deficit. So this line right here is the level that you were consuming at. So you're still in a caloric deficit at the 6-month mark, but then you start to get to the 9-12-month mark, and then you start to see this weight start to creep up because you're back up to your normal habits. Your normal habits, which you were at before, which is what was leading you to gain weight, you start to increase back up to that in terms of your energy intake. So your weight starts to creep back upwards. And one of the difficulties is it's not a mathematical model. You can't just say, well, drop energy intake, body weight goes down. Now if I just go back up to where I was, which technically led you to start to gain weight in the first place. So technically your baseline should have been a little bit lower than that. But that aside, it's not that simple, right? You're dropping your energy intake. Your energy expenditure drops a little bit to compensate. So your body starts to reduce the energy expenditure. You start to fidget a lot less. You're less physically active in general. And the big thing is that your appetite increases so much. You drop your energy intake, your appetite rises, and you start to look at food very differently. You start to get more cravings. You start to want to eat more. It's becomes a lot more difficult to maintain that weight loss because your body starts to fight back. It drops your leptin levels. Your insulin levels are certainly lower. You have higher expression of these different hormones like AGRP. You have a number of different hormonal changes that occur over that time only because you dropped your energy intake. And just because you return, another aspect of this is just because you return back to what you were eating before, your appetite may still be elevated, meaning that your drive to eat may still be higher than what it was before, which leads to, again, another drive of weight rebound and maybe even weight regain and weight overgain, or you gain more than what you were before. So being cognizant of all these different of these factors is what ultimately can lead to successful weight loss. Actually learning how to regulate appetite, which is actually something that I've had a video in the works on this very topic for a very long time. And I had recorded it, edited it, and then I just thought it wasn't quite good enough, so I just scrapped it. Then I just redid it. And I'm like on the fence if it's good enough. But at some point I do want to make a video on how to regulate appetite, because I think it's one of the key aspects that a lot of people seem to fail to understand is super, super important. So energy intake drops, energy expenditure drops as a result as well, slightly. It's not the main factor, but it does drop slightly. And appetite increases, skyrockets. So now you have this boogeyman of appetite fighting against you, where you're constantly thinking about food, and you may eat a little bit more, like, oh, it's not a big deal, because it makes you feel better. And ultimately, as you go back up to that baseline, to the level that you were consuming, you start to creep back upwards in terms of body weight. So the bottom line is you can't return to the same dietary habits that you had at one point. If you're going to make a change to lose body fat, you have to tell yourself this is going to be for the long haul. This is going to be forever. Because otherwise, if you return back to your old style, your body just reverts back to where it was. And on top of that, you've kind of hurt yourself, because it takes a while for your appetite to regulate back down to where it was. And this is a concept known, there's set point theory, settling point theory, and the static model, which is another thing that I plan on creating content on, because each one of these models has different predictions for how appetite is regulated, energy intake is regulated, and energy expenditure. But that's for another time. Now, as a reminder here, this is for the carbohydrate-insulin model. One of the rebuttals that the conventional model brings up is that with this carbohydrate-insulin model, remember, we see drops in circulating metabolic fuels. So remember, it gets sucked up into the fat storage, which leaves the vessels more bare with circulating fuel. So you don't have as much glucose, you don't have as much of these lipids, these triglycerides and fatty acids and whatnot. And that's what leads to an increase in energy intake, and that's what leads to an increase in body weight. Okay, fine. So what the conventional model researchers point out is that there is a study that has artificially actually reduced the levels of these metabolic fuels. So these metabolic fuels are artificially reduced by this drug called acipimox. And acipimox is given to these obese individuals over 6 months. And there is a drop in free fatty acids. There's a drop in glucose, in fasting plasma glucose, which would go in favor of this carbohydrate-insulin model. It's like a artificial way of getting the same conditions. And then saying, do these people then gain weight? Do they end up consuming more and end up gaining weight? And the answer is no, they don't. So this is baseline placebo. So people that are given a fake treatment, baseline with the people that are eventually given acipimox. And then 6 months later, and we find that BMI is the same, lean mass is the same, And the visceral adipose tissue is also the same. Nothing changes. Across any of the measures, none of them change. So this is, again, another proof that even if you drop circulating fuels, which is part of this model, that doesn't actually seem to be the case. We're not actually seeing what is being predicted. And additionally, they also point out that in obese individuals and in diabetic individuals, the circulating levels, the serum levels of these, so to go in the opposite direction, the serum levels of these fatty acids, triglycerides, blood sugar levels, they tend to be elevated. They don't tend to be decreased. So why would these individuals that are obese and whatnot, why would they have higher levels than normal of all these different metabolic fuels, but the carbohydrate insulin model predicts that the fuels would be lower, and that's what leads them to gain weight? I guess you could argue that maybe there's a threshold, there's a cyclical pattern up until a point, and then the fat cells can't take on any more of the nutrients, and therefore you have elevated nutrients in the bloodstream. But then you're just creating more complexity onto the model. Not that you can't change a model. You should be able to change a model because you should be flexible with what the data indicates. But it's at least another small hole in the idea of the carbohydrate insulin model. And then finally, the next thing that they mention is, so they do a meta-analysis where they compare low-fat diets versus high-fat diets, low-carb, high-fat diets in energy expenditure. So returning back to that metabolism effect that I mentioned at the very close to the beginning. Remember when I mentioned this with the animals, with the ketogenic diet, they saw an increase in metabolism. And what they find is that, so these researchers, what they found is that there's actually a slight favor towards the low-fat diet, not the low-carb diet, in terms of a metabolic advantage, which we will return to this because this is something that as I mentioned, I was slightly convinced the opposite. And then when they compare the fat loss, they find that fat loss was more in favor of the low-fat diet and not the low-carb diet. Now, I should remind people that I understand if you personally have used a low carb diet and found it far easier for fat loss, that's not what these studies are saying. They're saying on average, people that were compared against, groups of people that were compared against one another, on average, they saw slightly better fat loss on the low fat diet. That does not, however, mean that a low carbohydrate diet can't be extremely effective and maybe on a personal level, may be far better than a low fat diet, high carbohydrate diet. That's the only point of this. It's not saying that low carb, I don't think any of these researchers would say that low carb diets don't work or that they don't lead to fat loss or anything like that. And we even saw that earlier with comparisons of the two diets. There were improvements in fat loss. So the next thing is a rebuttal of these meta-analyses by the carbohydrate-insulin model individuals. So the carbohydrate-insulin model researchers reanalyzed all the data that I just presented with this meta-analysis, which, by the way, the way to read them is to there's a lot more to this than what I'm about to say. So please excuse me if you're a statistician, but you typically look at the overall diamond, which is down here. So the overall diamond is taking into consideration all the results from all of these studies and putting it into one overall group effect and indicating which side of the line that it goes. And this side is the low carb side. I cut it off by accident, but this side is the low carb side and this side is the low fat side. And what they found is if they stratified studies based off of the length of the study, so if the studies were less than 17 days long, which is pretty short, then yes, there was a slight energy expenditure benefit towards low fat diets. So high carbohydrate, low fat diets. However, when they stratify towards more or greater than 17 days, here's the markers so you can read it, it suddenly switched to the opposite. So, right, so here it's to the left of this line, and now it's to the right of this line. So they're saying that there's a time effect as over time, and they predict it to be about 2, maybe 3 weeks, that you see an increase in energy expenditure. And thereby, you see a benefit in the lower carbohydrate diet. Now, the reason for that is what they speculate is because of ketones, so that it takes a while for ketone levels to increase, and it takes about 2 to 3 weeks for ketone levels to increase, and therefore you start to see this increase in energy expenditure. But initially, at the onset, there is no benefit of energy expenditure. There might be a little bit lower actually in the low carb group, but then over time it starts to pick up and it passes what was normally the case. So that's really interesting. I found that this reanalysis to be really fascinating. The other researchers, they don't quite agree, and they end up reanalyzing all this data, and they end up complaining that the carbohydrate-insulin model individuals, the researchers, didn't use all of the data that they could have, and that they specifically focused on one style of energy expenditure measure called doubly labeled water over using something like calorimetry, using like chamber calorimetry, which I'm not going to go into the differences between those two, but the point is that so this study right here is from the conventional model researchers, and this is what we were just looking at. This is in the carbohydrate-insulin model. So they reanalyzed this study and ended up determining that based off of a number of assumptions that they would love to have the data so that they could actually reanalyze it completely. But based on a number of assumptions, they came to a conclusion that there's a 70 calorie boost in metabolism with the low carbohydrate diet. And the carbohydrate insulin model individuals predicted 135 calorie boost in metabolism. Beyond that, these individuals also predicted, if you want to stratify it further, that for every 10% drop in carbohydrates that you consume, you see an increase of 50 calories in metabolism. So if you were to drop, let's say 30% of your carbohydrates, then you would see an increase of 150 calories. And let's say if you were consuming a lot of 50% carbohydrates, and you drop it to just about nothing, then you would see a 250 calorie boost. So it can be pretty substantial according to this calculation, but this calculation is far more modest. And they even say if there is even an effect, but based off of what they can see. So here, the point is that it does seem to be a little bit more in agreement. These people have changed their mind a little bit, like, okay, maybe there's a time effect, but they also point out that the ketone hypothesis doesn't make a whole lot of sense because there are starvation experiments where ketone levels increase, and they reach their maximal levels in a week, sometimes less. So it shouldn't take 2 to 3 weeks. And a week is still within this time period, less than 17 days. So why don't we see this effect in these in this analysis if that's the case? I think I would push back against that and say that one thing is if you were to consume a low carb diet, the ketone accumulation is slower than it is in starvation. If you don't consume anything, if you're fasting, that's the fastest way to increase your ketones. I've shown this in previous videos as well, ancient videos, but they exist. Unless I took them down, I don't know. I've taken down hundreds of videos because they were a whole different style, and well, I won't go into it. The point is that I covered a study where they measured ketone levels comparing low carb or ketogenic actually compared to a fasting condition, and they found the fasting condition just shot up in ketones, and low carb just slowly, incrementally increased. So I could see that in the benefit of the carbohydrate insulin model. Okay, so the last thing I wanted to discuss is the mechanism for that. So the reason why there's an increase in caloric expenditure in the increase in metabolism is due to the liver. So one group, the conventional model, they propose that it's because the liver now, because there's no glucose, there's no sugar around, and we need a certain amount of blood sugar, otherwise we die, the liver starts to produce more sugar. So it takes these glycerol molecules, these fat molecules, and starts to synthesize them and amino acids, and synthesizes them into sugar and then pumps them out of the liver. So gluconeogenesis. And that requires energy. So you're taking up energy to do that. Beyond that, they also say ketogenesis. So the production of ketone bodies also is another factor which leads to an increase in energy expenditure. And they say that's it. There's nothing grandiose about ketones. The carbohydrate insulin model, they mention that there's an increase in ketones, yes, obviously, from the liver, but additionally, it has an impact on mitochondria. And they don't specifically say this, but I covered a study a little while back, maybe a year and a half ago now, where maybe it was just a year ago, man, time flies, where there were some animal studies where they took away insulin and fed these animals, I think, a high-fat diet, or they exposed them to ketones, something along those lines. And they did see that it had an effect on mitochondria, specifically that it had an effect on changing the amount of uncoupling protein. Uncoupling protein is a protein that's found in the inner membrane of the mitochondria. I'm not going to go into too much detail with it, but it essentially makes mitochondria less efficient so that they have to burn through more nutrients to sustain the cell. And as such, if you're burning through more nutrients, then you're expending a lot more calories. So, or a lot more energy in general. So that's a mechanism, not something that they mention. It's just something that I ran across in my readings. So I think that's a plausible explanation. But they also mention that ketones may increase mitochondrial biogenesis, so the synthesis of more mitochondria may lead to changes in hormonal profiles. And they also mention, obviously, satiety effects, but the satiety effects are not going to have an effect on energy expenditure. It's just going to be something separate. That there's also a benefit of ketones in that it also increases satiety. So the mechanisms are also different. They both originate from the liver, but then they diverge in terms of their overall effect, or at least the predictive effects. Okay, wow, that was a lot. I felt like I ranted a little bit there, so my apologies. So in general, this is the midpoint conclusions, although I had a lot more to say than what is written here, that's for sure. The carbohydrate insulin model believes that carbohydrates, especially high glycemic carbohydrates, causes rises in insulin, which partition nutrients favorably towards fat cells, leaving other cells devoid of nutrients and thereby making us eat. Because as they're devoid of nutrients, they indicate to the brain, hey, we're hungry, we need more energy. And then the brain starts to give the signals for hunger. So through those hormones that I was mentioning, the AGRPs, the neuropeptide Ys, which then lead us to want to eat more. The conventional model believes that the overconsumption due to food environment, so specifically like processed foods, hyperpalatable foods, things of that nature. Genetics is another factor, although a smaller factor. And other variables, they mentioned like brain injury and things like that, but how often are people undergoing brain injury leads to fat gain. So overall, the overconsumption, but that could be it's mostly due to food environment and genetics. So it's not just a calories in, calories out, even though that is the backbone. There's a lot of physiology that's stacked on top of that model. Okay, and next I'm going to be covering dietary recommendations according to the carbohydrate-insulin model, although some of these recommendations I would say definitely fall in favor of the conventional model as well. So if you're interested in accessing that, then certainly hop on over to the Physionic Insiders program, join there, and you'll get access to this full version as well as many, many other benefits along with live sessions with me, seminars, research reviews, shortened summaries of data, and a bunch of stuff. It's a fun time and a community where you can engage with me. All right, with that, thanks for your patience getting to this point. It's over an hour long, and I'll hope to have the pleasure of speaking with you in the future. Actually, let me know your thoughts. I would really love to know that as well. If you still follow the carbohydrate insulin model or the conventional model or somewhere in between, and why. And if you have any critiques of this, make sure that it's about the data. Be sure to point out, like, maybe they missed this or maybe they missed that. And of course, I'm only showing you snippets of data from some of the studies that I mentioned. So there's a lot more to cover as well, which is something that I hope to do in the future as well. Okay, now that's it. I'll let you go. Thanks for stopping by. See ya.